Hey everyone, today we're going to be talking about limits, which is a basic and foundational, course and concept that everyone needs to cover before they talk about calculus or get into something complicated like differentiation or integration. Limits is like the foundation that enables us to understand what those super complicated concepts are and how we can solve those questions. So let's dive right into it. Just this video is going to be about the introduction of limits, and we're going to cover some basic examples on understand limits how they work. Right. So we're going to start with Zeno's paradox, and let me tell you a little about this guy Zeno. So he was a Greek philosopher, and like a lot of Greek philosophers, he posed a lot of interesting and important questions, and posed them as in the paradoxes, right? So one of the questions that he asked was that, say he's at this point, start, and let's say the royal garden is 100 meters away, and that's point N, right? So he said that, if it's 100 meters away, I will first have to cover half of that distance, which is going to bring me to 50 meters, which means that it's going to be 50 meters till I get to the end point. Then he said that, okay, now I'm here. At this point, I need to cover half of that distance, half of the remaining distance, which is going to bring me to this point, which means that I'll be 25 meters away from the royal garden. Then half of that, 12.5 meters. He said that, I cover half of these distances, but I would never arrive at my point because, half of some distance that I covered would still be left. And, this puzzled a lot of mathematicians, a lot of philosophers at that time, and but obviously it's a paradox because it makes sense that if you're walking towards a particular destination, then you will reach the destination eventually, right? It makes sense. So this paradox can be understood better by the use of limits. So let's look at one example. All right, let's say I have this graph here. And I bet a lot of you recognize this graph here. This is for fx is equal to x squared. And if I were to ask you, hey, what's the value of fx or y when x is equal to 3? So you'll just plug in here f of 3, that's going to be 9, right? Which makes sense because at x is equal to 3, the corresponding y value for this function is going to be 9. Right? That's how you study graphs. So, but okay, what if I ask you, what is this? This is LIM, the short form for limit. Limit of fx when x tends to 3. This is an arrow, so x is approaching 3. And you may ask that, oh, well, x is approaching 3 from which direction? Is it from the left hand side or from the right hand side? Right, it makes sense because you can approach 3 from this side or from that side. So, let's go with the left-hand side for now. So for that, what does that mean? So it means that if you were to use values such as 2.99997, 2.99998, 2.99989, and you plug them in the function here, what are the values that you're going to get? Which are going to be super, super close to 9, right? And then for the right-hand side, I just made this a positive sign, so this says 3 plus. And I plug in values like 3.00003, 3.00002, 001. And I see that those values are also going to approach this value of 9. So, then you might say that, what's even the point of limits? Like we were studying limits, sure, we were seeing what, happens to the function when x is approaching 3, but why don't I just plug in the value 3 and see for myself? Okay, let's look at another example now. Let's say I have this graph here, and I have this function, right? And this is the function fx is equal to x minus 1 divided by x squared minus 1. Now we all know, I'm assuming we all know that at x is equal to 1, this function is going to be 0 over 0, which is undefined, indeterminate. So we can just plug in the value for f of 1 here to see what what's going to happen. What is the value that this function is going to approach when x tends to 1, right? So let's just do this. And we put a circle here, an empty circle, which denotes that this function is discontinuous at x is equal to 1, which means that it's not gonna take in any values for x is equal to 1, right? So at this, we can just, one way is to just look at the graph and see that, the value is going to be 1/2, right? And another method is to use limits. So if I ask you limit x tending to 1 f of x, from the left hand side, if you plug in values like 0.99998, 0.9999, you're going to see that it's arbitrarily close to 1/2, like super close to 1/2. And from the right hand side, 1.00001, that's also going to be super close to 1/2. So you can make an intuitive decision that this value, finally, is going to be 1/2. But you cannot make the same claim for f of 1, right? Because that's going to give you 0 over 0. We're going to get into how this works and what's the algebra behind this. We're going to get into that a little later. But before that, let's look at one last function before we discuss a different concept. And trust me, this function is extremely important, and I would advise all of you to pay a lot of attention to this particular function. So this function is fx is equal to sine x over x. And if I were to ask you, what is f of 0? Again, it's going to be 0 over 0, because sine of 0 is 0, and x is equal to 0 is obviously 0. So that's, again, undefined, right? But, so again, you can see the empty circle there. That's for, when the function is not defined at a particular point. So, looking at the graph, this value is going to be y is equal to 1. Which, just looking at this function doesn't make a lot of sense, right? Because you're saying that sine x is equal to x when x is super close to 0. Which, does not make a lot of intuitive sense. So, how do we write this out? We write it as limit x tending to 1 sine x over x, or you can write fx, sure, is sine x is equal to 0. X tending to 0 is going to give you 1, right? And this is an important limit, right? So now we know how limits work and what they function, that you're approaching a particular value. X is approaching a value, and you're trying to find what happens to the value of y, or like f of x, right? The function. So I discussed a concept here, right? The left-hand limit and the right-hand limit, that concept just now. So left-hand limit for a function f of x, right? It's denoted as this, limit x tend to an arbitrary constant as a, and since it's a left-hand limit, we put a negative sign here, f of x. And for RHL, it's just going to be limit x tend to a plus, sure, of f of x. And let's say these two values are L, another constant. So if we know that the left-hand limit and the right-hand limit are both approaching this quantity L, then we can conclude that this is also going to give us L. And if you see carefully, I have not put any sign here, which means that the limit when x approaches a particular number, a, right, it's going to be L. And it can go the other way around too. It's you can see the two arrows here. So it means that if we know that x approaching, say for this function, x approaching 1 f of x is going to give us 1/2, then that means that the left-hand limit and the right-hand limit are also going to approach 1/2. So this means that if these two numbers are not equal, then this is not going to give us L, right? We cannot make that conclusion. So let's look at an example now. And in this example, I will show you guys how we do algebra with limits. All right. Let's say our function here is fx is equal to 2x over x minus 3. All right. So let's try and find the left-hand limit first. So that's going to be limit x tending to at 3. All right. So that's going to be x tending to 3 minus 2x over x minus 3. And now I'm going to try to simplify this and in a form that some of you might find confusing, but I'll talk about it in a bit. So I'm saying limit h tending to 0, 2 of, now obviously I'm not using x now, so my terms are going to be in terms of h now. So this means this is going to be 3 minus h over 3 minus h minus 3. Now, one thing that you really need to remember is that when you make this transformation, since we're dealing with the left-hand limit here, this means that we're going to put this number a, whatever a you're tending to, so let's say x is tending to a, minus, that would imply h is tending to 0, would give us, wherever you have x, that's going to be replaced by a minus h. Alright? So, similar logic. Here, x is tending to 3 minus, we make this 3 minus h. And when we solve this, we're just going to get limit h tending to 0, 6 minus 2h, divided by 3 minus h minus 3 is just going to be minus h. And, you know, this can be, when you plug in the value 0 here, you're going to realize that this is going to give us 6 minus 0 over, you know, this negative 0, right? Which doesn't make a lot of sense, but this negative sign is like super important here, because what this means is that this is going to be just this. I took this negative sign outside the limit, and you can do that. We're going to cover that later in limit laws when we discuss certain limit laws. So this, as we know, is going to be 6 over 0, which is infinite. So this limit is tending to negative infinity because of this negative sign, right? So now we know the left-hand limit is negative infinity. Okay. And one thing, I don't know if you noticed that, is that we got something like 6 over 0. We did not get something like 0 over 0, which we were getting for these different functions, which is something that we'll get to later as well. Alright, let's find the right-hand limit now. So that's just going to be limit x tends to 3 plus 2x divided by x minus 3. So now, let me ask you, if I were to replace x by h again, what do you think is going to be the value for x now? Because, you know, using a similar logic as this. It's going to be 2 times 3 plus h divided by 3 plus h minus 3. This is just going to give us limit h tends to 0, 6 plus 2h divided by h. This is different from the limit that we got before because we do not have a negative sign. So if we were to evaluate this, we're going to get something like 6 over 0, which is positive infinity, right? So now we know that LHL, the left-hand limit, is equal to negative infinity, and the right-hand limit is equal to positive infinity. So can we make a conclusion about what happens to this function when x tends to 3, right? The overall final conclusion that we made, because you have the left-hand limit and you have the right-hand limit, and then you have the final, final answer, right? So that you cannot determine, because if you remember the theorem, the property that I told you about before, it says that only if LHN and RHL are equal, they converge to a particular limit, then we can say that the overall limit is going to be that L, right? But now, as you can see, they approach to different values here. So we cannot make that conclusion. So we say that the limit does not exist. Finally, we're going to talk about an easy concept, and it's not like, it's super straightforward to understand. This concept is of vertical asymptotes. And basically what this means is that for what values, so if I have a function, right, fx is equal to, let's just use the function that we used before, 2x over x minus 3. Vertical asymptote mean, for this function, the vertical asymptote would be the value of x for which this function is going to go to infinity, alright? And we know that if we plug in x is equal to 3 here, that's going to give us 6 over 0, and that's our vertical asymptote. So for this function, the vertical asymptote is x is equal to 3. Let's look at another function. Let's call it g of x. is equal to tan x. Now I'm not sure how many of you are familiar with trigonometric functions, sine, cosine, tan. These are like the most important ones. And if you're not aware of like the key values these function takes and for like different degrees, different radians, then you should definitely look into that, because we're going to cover these functions in detail in the future videos. So what this means is that for finding the vertical asymptote, you're just going to say, for what value is x, is my y going to be infinite? And that's just, if you remember your trigonometry, it's going to be x is equal to pi over 2. So that's your vertical asymptote. It's just the x value for which your function is going to approach infinity. So that's all the concept that we're going to cover for this video. We're going to cover some more functions and some more interesting things that we can do with limits in the future videos. We're going to go over limit laws, we're going to go over some important theorems, and alright, I will see you in the next video.